Continuing on here, some chapter 9, I think. Yeah, chapter 9. So last time, before we took the exam last week, we did a little intermolecular forces, I believe. And remember, intermolecular forces are the forces that hold one molecule together with another molecule. And it could be two of the same molecules, two different molecules. All intermolecular forces, as we talked about, are pretty much a very basic interaction that occurs. Pretty much the positive side of one molecule is attracted to the negative side of another. So, sort of an electrostatic sort of attraction. And that's pretty much the forces that hold, like I said, like say water molecules with other water molecules with different types of molecules, are these intermolecular forces. So we talked about a few different types. We talked about dipole interaction, and that is really the main force there for polar molecules that cannot hydrogen bond. And if you have a dipole moment, you are a polar molecule, and essentially you got pretty much the same setup as above. You always have a positive side to that molecule and a negative side to that molecule because of the unequal sharing of electrons within that molecule, and you always have a way to interact with one another. We also talked about something like ion dipole. Ion dipole is really what happens, for example, when you dissolve a solute in a solvent. So if you have an ionic compound, it is going to be an ion attracted to, in this case, the negative side of a polar molecule. So if you got an ion and a polar molecule, they will have that sort of attraction there. That's again how, for example, water surrounds all the ions when you take something like sodium chloride and want to dissolve it in water. We also talked about hydrogen bonding, and that is the main type of interaction for polar molecules that can hydrogen bond. So remember that in order to hydrogen bond, you do need a bond between hydrogen and some electronegative atom like nitrogen, oxygen, or fluorine. So you need a hydrogen that is directly attached to those. Again, on the periodic table, that's our three kind of big electronegative elements up there. And that's going to create a really good polar bond, which is going to create a separation of charge and allow them to interact with each other. And that's what happens in water. Water has obviously a couple of hydrogens directly attached to an oxygen, making this a very polar bond. And it can obviously do the same deal over here, negative and positive, and that allows it to hydrogen bond. So again, just because you have a hydrogen doesn't mean it can hydrogen bond. It does need to be directly attached to one of those three elements in order to participate in hydrogen bonding. We also talked about dispersion forces. And we could get dispersion forces, which is the main type of interaction for nonpolar molecules. So nonpolar molecules are basically rolling with dispersion forces. They are very weak. They're very temporary. That fell under there. We could have ion induced dipole. We could also have dipole induced dipole. And that's pretty much the deal. Like if you have a nonpolar molecule and you roll up an ion next to it, temporarily the electrons in this guy are going to be attracted to that ion. And now you will get a separation and charge in that nonpolar molecule in a way for those to temporarily sort of interact with one another. You could also have what is known as an instantaneous dipole. And in an instantaneous dipole, what happens is you could have this with two nonpolar molecules. They both have no charge, but because the electrons are moving around, all the electrons can sort of migrate to one side of the molecule versus the other. That will temporarily cause that nonpolar molecule to temporarily have a charge, which then can kind of do the same thing for the other nonpolar molecule. And now you have two nonpolar molecules that normally don't have any type of charges, temporarily gain these charges, and now they have a way to interact. That interaction is really weak because as soon as those electrons kind of move back into their normal sort of orientation, it's going to kind of fall apart and they have to rely upon new sort of interactions to occur. They can't maintain those over a long period of time, and that's why they're very weak. In terms of strength, the hydrogen bonding is the strongest type of intermolecular force. Dispersion forces are the weakest type. And intermolecular forces play a really big role in a lot of things, including things like melting points and boiling points. So things with really strong intermolecular forces, things that could typically hydrogen bond, for example, typically will have higher melting points, boiling points, because they're held together tighter, which requires you to put more energy in there to break them apart, say into the gas phase or something like that. And that translates into a higher temperature. Things that use dispersion forces, like, for example, methane or something like that that comes out of the gas pipe there. They use these dispersion forces, which is really weak. Doesn't take a lot of effort to get them to kind of melt or kind of go to the boiling point because there's not a lot of attraction that's there. In terms of dispersion forces, one of the things we did talk about was that it does increase in strength with increasing molar mass. So if you're sort of comparing two nonpolar molecules and you want to know maybe which one has a higher boiling point or melting point versus the other nonpolar molecule, the one typically with more molar mass will typically have stronger dispersion forces and would have the higher sort of melting point, boiling point in comparison to the other nonpolar molecule that is present. Um, and that's because with higher molar mass, more atoms, more electrons, greater opportunity for everybody to interact, more places for everybody to interact, and more chance for polarizability, which is the electrons going one way or the other, more chance of that occurring. Any questions on any of that stuff? The other thing intermolecular forces are really important for, as we will talk about, is things like solubility. Things that use similar type of intermolecular forces will be soluble in each other. Things that use very different types of intermolecular forces will not mix usually very well with one another. All right, so continuing on, we're going to talk a little bit about the liquid state and some of the states of matter. In the liquid state, molecules are really close together. They do have a little bit more room. They're not super tight, if you will, but they also have a little bit more energy than they do, say, in the solid stage. And that's why liquids are fluid, because they have enough energy to pass one another, those molecules, as they're in the liquid state. They remain in motion. Viscosity is the resistance of a liquid to flow. It is related to intermolecular forces. Things like water has a low viscosity, motor oil has a high one, and it decreases with temperature as well. Now, when we talk about water, there's a couple of types of forces and things that we see occur. Cohesive forces are the forces of attraction between molecules of a single substance. So comparing like hydrogen bonding in water, so water and water sort of interactions, similar type of ones. Adhesive forces are the forces of attraction between different molecules. As we'll see, this is why, for example, we get like a meniscus in a glass tube. And that's because the attractive forces between the liquid and the glass container may be higher than the attractive forces between the liquid and itself. And that causes a little meniscus to sort of happen. Surface tension is the elasticity that's found on the surface of a liquid. Energy is needed to expand the liquid's surface. It is higher in liquids that have greater intermolecular forces. So, for example, if you can lay a paper clip on some still water and that will keep it there. The surface tension will be greater in water than other liquids because of the hydrogen bonding that occurs, which is a really strong force. It's also why some bugs, right, can just walk over the water, right, and no problem and stuff like that because of the surface tension. And as we'll see in a better picture maybe in a second, but if you think about sort of the water molecules at the surface versus, say, a water molecule that's underneath the surface, the water molecule underneath the surface is going to feel the attraction to all those water molecules all around them. At the surface, what happens is water molecules will feel attraction kind of to the left and right and also downward, but there really is no sort of attraction above each of those liquids or those molecules. So what that does is kind of stretches it out the surface and down, and there's nothing kind of attracting it upward. So it creates that sort of surface tension that occurs, as you can kind of see here again. The attraction on the top layer is kind of left and right and down, as opposed to something in the middle where it's going to feel sort of, let's say, equal attraction, but attraction all the way around the molecule. And that is what kind of spreads out the surface. Now, when we talk about soap, soap is a really like an organic type molecule. And what makes something soap, for example, is it typically has a really long chain of carbons and hydrogens. And I'm just going to represent that sort of on what's referred to as line structure. These are all carbons here. And there's basically hydrogens attached all the way across here. And at the very end, there is this sort of group here. So when you look at soap, soap has basically two parts. It has this part, which is all carbons and hydrogens, and that is definitely nonpolar. And that is what is sometimes referred to as the nonpolar tail of soap. And over here, which is based off of carboxylic acid, which is an organic molecule, this is what is sometimes referred to as the polar head of soap. And that works really well because, for example, dirt, for the most part, is nonpolar. So when you use soap, what happens is the nonpolar part of soap aligns itself and mixes really well with that dirt because it's also nonpolar. So both of those nonpolar parts work really well. And when it does so, it aligns the soap molecule with its polar part sort of on the outside after it traps in all of your dirt. And that's really good because usually when you use soap, you follow it up with some water, which is polar, and you wash it off with some water, which is polar. And because the dirt's trapped on the non-polar part and you wash it with water, out goes the dirt with the soap, right? And you're clean at that point. And that works really well. Obviously, if you have soap molecules, it's able to do those hydrogen bonding. And that's also what happens is it has the ability to break the surface tension of water. If you just throw water on your car or like an umbrella, and especially maybe it's got some wax on it or something like that as well, you will notice that the water will just kind of bead on there and it really won't spread out. And it doesn't spread out until you sort of add some soap to your water there as you're washing your car. And that allows really the water to kind of spread out. And that's because what happens is the soap molecules get in between the surface water molecules, and that breaks those bonds and allows the water molecules really to kind of spread out. And that's why obviously when you soap up your car, it just kind of spreads out over it, rather than if you have sort of a freshly washed car or something like that and you hit it with the water, it will typically just bead. It typically just beads because wax and stuff like that is non-polar and water is polar, so they don't mix. So it just ends up beading on the surface of your car if you have a really good wax job. If you don't, you typically will be able to see the water bead typically on your car. Now, when we talk about adhesive and cohesive properties, that is, as I mentioned earlier, really why we kind of see a meniscus and we look at the meniscus. And that is because what happens is we get sort of capillary action happening. And capillary action is when we have a small diameter sort of glass tube. For example, water will just rise up it through that sort of attractive forces. So when we look at the meniscus, as I mentioned earlier, what happens in this particular case is, say for something like water, the attractive forces between water and the glass tube are actually stronger than the attractive forces between water and itself. So what happens is the water that's in contact with the glass will rise up the glass through capillary action. And that is what's creating that meniscus that we look at. That is also why when we read a meniscus, typically in this U shape, we read from the bottom of the meniscus. And because the bottom of the meniscus, right about here, is not touching the glass. So it is not experiencing that capillary action that's drawing it upwards. And if we didn't have that interaction, all the water on the sides here would actually be right about there in terms of the level. So that's why we kind of read from the bottom of the meniscus. In this case, the adhesive forces, the forces between two different molecules, the glass and the water, are stronger than the cohesive forces, the forces between water and itself. Now, I would say in most cases, that is typically what you see with your meniscus is this U-shaped, but there are certain chemicals or elements that, for example, mercury actually has the meniscus that goes the opposite direction. And in this case, what's happening is the cohesive forces, the attraction between mercury and itself is actually stronger than mercury and the liquid. Mercury and the container, the glass container. So what happens through capillary action is it actually comes in on itself and creates this upside down meniscus where we would actually read from the top of the meniscus in this case, because without that attraction, the true volume is actually right around there. So mercury is a very common example that does it, but I would say 99.9% of the time, you're going to see the U meniscus going in that normal sort of direction where you read from the bottom. But it is possible to have a meniscus that actually goes the other way, and that just means the cohesive forces, again, are stronger than the adhesive forces in this particular case. Any questions on that there? Now, vapor pressure is the pressure that occurs above a liquid. And at the surface of any liquid, what you have happening is you have liquid molecules jumping out of the liquid, and you have slower moving gas molecules dropping back into the liquid phase. So at the surface of a liquid, you do have this common exchange of stuff going out of the liquid phase, guys slowly moving, dropping back in until it reaches equilibrium. And when it does so, because you have these guys coming out, you will end up with some vapor molecules above the liquid or gas molecules above the liquid, and that will result in the vapor pressure above the liquid. In an open container, liquid will evaporate completely because air diffuses it as it's doing that. So for example, if you spill just a little bit of a drop of a liquid, say on the bench top, you will have this process occurring where basically we have evaporation occurring, and we also have some condensation occurring coming backwards. But what happens in this situation is we have it happening all over the place because it's a big surface area. And we do have air that comes by and blows these molecules away. So what ends up happening is because that air is blowing the molecules away, you end up with a greater rate of evaporation than you do condensation. And there's not as much molecules in the vapor allowed to come back in. And eventually, right, your little puddle kind of evaporates away, right? And it will evaporate away much easier. Clearly, though, if you threw some water into a beaker, it would take a much longer time for it to evaporate in an open container. It will still do the same thing. You'll have some evaporation happening, you'll have some condensation. You will also have the air that will push it away, but there's a lot of under the surface molecules that are not evaporating yet, right? So you have to wait until kind of the top layer starts to evaporate to allow new ones to get to the surface and evaporate. So it's going to take much, much longer for say, a liquid in an open container to evaporate than if you had just a little bit on the bench where it's really spread out and you got a big old rate of evaporation. Now, the pressure of that vapor above the liquid when it reaches equilibrium between evaporation and condensation is known as the vapor pressure. Liquids with really high vapor pressures are said to be volatile. That means they go into the gas phase pretty easily. In order to have a high vapor pressure, that would imply that above the liquid, you have a lot of gas molecules, right? So if you know a way you could get a lot of gas molecules is they have to evaporate pretty easily, and that is why it's known as being volatile. A lot of organic compounds are very volatile. They could go from the liquid phase to the gas phase super easily. That's because they're also held together by dispersion forces, which are very, very weak. So it doesn't take a lot for them to start to evaporate and go into that liquid phase. The vapor pressure of a liquid at a given temperature is determined by the intermolecular forces that act on it. If you have a large or strong intermolecular force, you will typically have a low vapor pressure. That is, again, because everybody's held together tightly. There's not going to be as much evaporating to cause gas above the liquid, and you'll end up with a smaller vapor pressure as a result of that. Now, if you take a liquid and put it into a container and you actually put a lid on it here, and if you take a look at kind of where the liquid was to begin with when you put it into that container, what will happen in this particular case is you definitely will have a pretty good rate of evaporation happening here at the beginning. So you're going to have all these guys evaporating. The deal, though, is unlike an open container, it's got nowhere to go, basically, right? So you got nowhere for these guys to go. So eventually they're going to kind of work their way kind of back down and back into the liquid layer. And you're eventually going to get some guys starting to go through condensation, dropping back into the liquid phase. And eventually the rate of evaporation will equal the rate of condensation, and you will reach equilibrium, which is what you see over here in this particular guy. And you will have some vapor molecules or gas molecules above the liquid, which is causing the vapor pressure. And what you'll also notice typically is if you take a look at where the liquid volume is now, it typically is a little bit lower than where it started from. And that's because when you first put it in there, you had no evaporation. And obviously, as it's been sitting there, you're going to lose some of those liquid molecules into these vapor molecules that are now flying around above the liquid. The result of that is we're going to have a lower liquid level here in the flask. Any questions on that there? We could actually calculate things like the vapor pressure, and we could use the Clausius-Clapeyron equation here. And this is the natural log of the vapor pressure at one temperature divided by the vapor pressure at another is equal to the delta H of vaporization. The delta H of vaporization is the energy needed to basically do one of two things: either take a substance from liquid to gas or go backwards, take a substance from gas to liquid. By the way, that occurs at the same temperature. That is the normal boiling point of that substance is where that occurs. For water, for example, that's 100 degrees Celsius where that occurs. At exactly 100 degrees Celsius, the delta H of vaporization for water is something like 40.7 kilojoules per mole, and that's what's here. R is actually the gas constant that involves energy, is the 8.314 joules per Kelvin per mole, and these are our two different temperatures here. So if we take a look at one here, and again, we could call this guy here T1, which is 25 degrees Celsius. That would go with our P1, which is 23.8 torr. And we have a delta H of vaporization that is 43.9 kilojoules per mole. We want to calculate the vapor pressure. We'll call that P2 when the temperature is 65 degrees Celsius. So we could use the equation that we have here, which again is the natural log of P1 P2 is equal to delta H of vaporization over R, 1 over T2 minus 1 over T1 in this particular case. Again, like normal, we do need some Kelvin because of our R constant. So like normal, we do need our temperatures in the Kelvin. So if we calculate that, that's going to give us a 298 Kelvin there, and 65 plus 273, 338 Kelvin here. We could actually leave our vapor pressures in torr. Should come out okay. So we'll go natural log of P1, which is 23.8 torr, divided by P2, which is what we're looking for. I'm going to take my delta H of vaporization. I'm going to multiply it by 1,000. And the reason I'm multiplying it by 1,000 is it will turn it into joules in this case. And the reason I'm doing that is my R value is actually in joules. So if you don't convert one to joules or kilojoules, you're going to be off by a factor of 1,000. So since my R value is in joules, my energy value here is in kilojoules. I'm going to multiply that by 1,000 just to get everybody in the right units. We go 1 over T2, which is 338, minus 1 over 298 there. So we can complete the right-hand side here. We'll take 1 divided by 338 minus 1 divided by 298. We're going to times it by 43.9 times 1,000. We're going to divide it by 8.314. That's going to give us the natural log of 23.8 torr over P2 is equal to negative 2.096918. To get rid of the natural log, you're going to do a little E action on both sides there. That's going to get rid of the natural log. And we'll do an E on our calculator if I can find it. There it is. And that's going to get me, maybe I'll go up here, 23.8 torr over P2 equals 0.12283. I'm going to multiply this to the other side. I'm going to bring this guy to the back and divide. And that should get me 23.8 torr divided by 0.12283 equals my P2. And that should hopefully give me the answer I see on the bottom there of 194 torr in this case. Yeah. First off, any questions on that there? What do we see in this calculation? We see in this calculation what we hopefully would expect. Our temperature went from 25 degrees to 65 degrees. We increased the temperature, which should increase the energy and allow more molecules to escape the liquid and end up in the vapor pressure or the vapor area. And because we have more gas molecules in the vapor above the liquid, that should translate to a higher vapor pressure. And we definitely see a much higher vapor pressure at the higher temperature than we do at the lower temperature, where there's less energy and less number of molecules that can escape. Any questions on that calculation there? So let's talk a little about some of the other processes that we do. Let's talk about boiling. Boiling a liquid. So when we take something like liquid water and we heat it to a high temperature, we start to get bubbles that form in it, and that's bubbles of water vapor that form beneath the surface of the water. These bubbles escape, and we say that the water is boiling, but not all bubbles make it to the top, right? And that's because the pressure outside of the bubble versus inside is greater, then it just pops, right? In that case, if you finally get everybody boiling, where the pressure inside and outside are equal to each other, or maybe slightly bigger for inside. That's going to allow that bubble to make it to the surface there to actually start boiling. You may also notice that sometimes when you go boil something and you hit it with the fire right away, you see a bunch of what appears to you maybe as bubbles. And you go, looks like my water's starting to boil right away. And it's really not. What you're actually seeing there is the CO2 molecules being less soluble in that high temperature coming out of the water really quickly. Clearly, it's not boiling. You can put your finger in there. It's still going to be really cold if you just put the fire on. It's not really boiling until you see, like we see over here, these big bubbles, right? That really start to make it to the surface. Obviously, when they get to the surface, they're going to sort of pop as the pressure change is different, and that's going to release our vapor, right? Or steam that we see happen, right? When we start to see water boil in that particular case. So at lower temperatures, like I said, the pressure inside the bubble is going to collapse. It's really not boiling. At what temperature something boils does depend on both the temperature and the pressure. So if you play around with the pressure and stuff like that, you could get things to boil at a weird temperature than it normally would. So pressure and temperature does play an important role on sort of when something may boil or not. Now, raising the pressure increases the boiling point. So that is something like a pressure cooker. You put the lid on with a lot of pressure. And with that tight lid, the pressure cooker holds the pressure on the vapor above the water, and it results in an increase in the boiling point of water. So we have this really high pressure. So instead of boiling at a normal 100 degrees, your water, because of this change of pressure, needs to boil at 120 degrees. And that's sometimes very good in terms of maybe cooking as well. Lowering the pressure typically will also decrease the boiling point. So if you have a little bit lower pressure, it's going to lower that boiling point as well. Boiling, as weird as it may sound, is actually a cooling process, even though you can burn yourself while you boil water. But it actually is a cooling process. And it's a cooling process because just as quick as you heat it from the bottom, it's actually cooling itself off from the top. That's why if you ever look at a thermometer in the lab, it doesn't go very much over 100 degrees, maybe 102 degrees Celsius. That's because technically if you hit the boiling point, it shouldn't continue to rise, right? So it should stay at 100 degrees Celsius in an ideal situation. That's why you never pop your thermometers if you put it in boiling water, because it shouldn't continue to rise at that point. And that's because even though you're adding a lot of heat down here, you are losing a lot of energy out the top of it. And that's why we again hit that sort of constant boiling point. It doesn't just continuously rise when we're at that boiling point. So the process of molecules converting from liquid to gas is known as evaporation or vaporization, and that is an endothermic process. Again, endothermic meaning obviously energy is absorbed. So as we go from liquid to gas, that's evaporation. That requires you to do what we just saw in the previous picture, which is heat it up, add energy in to get it to boil. Condensation is when gas molecules are converted to liquid, and that is an exothermic process. So exothermic is when energy is released. So if you think about that, you have gas molecules to start with, which are flying around with a lot of energy. And as you release that energy, those gas molecules now are going to fly around a lot slower. And when they come in contact with other gas molecules that are also moving slower, they may not have enough energy to get away from each other. And they're going to kind of collect and drop into like the liquid phase because they don't have enough energy just to bounce off. They kind of grab onto each other and go through condensation. At the surface of water, there's a constant exchange, as I mentioned, molecules jumping out of the liquid phase, gas molecules dropping back into liquid phase. Eventually, the rate of that happening, a rate of evaporation and condensation will equal each other. and equilibrium will be reached. That is what happens at the normal boiling point of a substance as you go from liquid to gas or gas to liquid. That occurs at the same temperature. And again, for water, that's 100 degrees Celsius where that occurs. You actually have both things happening at the same time. You have liquid water and you have water vapor happening at the exact same time. It's not until you get a little bit above 100 degrees Celsius that you actually do change into gas. It's not until you're a little below 100 degrees that you're into the liquid. So right at 100, you have basically both phases happening at the same time. So as the liquid molecules escape the liquid, they take their kinetic energy with them. And the result of that is the liquid actually is cooled. The result of that is when they're finally able to get to the surface and go from the liquid phase to the gas phase, they needed a lot of energy to do that, which means as they pop out into the air, they're actually moving a lot slower than air molecules. And that is going to decrease the overall kinetic energy of the surrounding air as well. So as a result, the net here is actually a cooling process, even though, again, we think of boiling as obviously a very hot process, but that is what is going on there. As water cools, the evaporation rate decreases, and we can maintain the evaporation rate with contact on a warm surface. As you hopefully know, heat and energy for the most part moves from hot to cold, right? That is sort of the flow of heat that happens. That is also why, right, we sweat when we are hot. Is a process to cool us down. And that is evaporation, right? Because on our skin, we put some water, our skin is going to release energy into the water that's on it. And for our skin, it's going to be exothermic, which means our skin is releasing all that energy. Now our skin feels, kind of cold as that's happening, right? That's going to be endothermic for our liquid and cause it to absorb all that energy and start to evaporate. So that is why, again, as we start to sweat, it's going to increase the rate of evaporation and ideally cool you down by increasing that rate of evaporation as you do that. It's also why you feel really cold when you get out of the pool, right? You got a lot of water on your body. You have a great amount of evaporation happening in your body, and a lot of your body heat is being used to evaporate off that water. The result of that is you feel really, really cold when you do that, right? Any questions on that there? Now, at the surface, condensation occurs as slower moving water molecules kind of collide and stick together. So fast moving water molecules tend to bounce off each other, but these kind of slower moving ones will sort of congregate together. And condensation is sort of a warming process in that effort. And if you think about it, right, when you're taking, say, something like a hot shower and you have a mirror in that room, right? The mirror gets really wet, right? And it gets really wet because condensation is occurring. And condensation is an exothermic process, which means as all that water is condensating on the mirror or wherever else in the room, it is releasing a lot of energy in that room. And you standing in that room taking a shower feels really warm because your body is now picking up all that energy from the condensation that's occurring, and you feel warm while you're in the shower, right? When you shut the shower off, you no longer have that, and now you're standing there all wet. And we go back to what has happened on the last slide. You're now going to have a very increased rate of evaporation again on your body, and that's why you start to feel cold afterwards, right? So that's why condensation is happening in that room, especially if you have a lot of hot water in a room that's going to go through condensation. That's why you feel warm in there as well. Also, why I like in a steam room or a sauna and that type of stuff, you feel that warming process that occurs. And as I mentioned earlier, there is a certain amount of energy that's required to do nothing more than take a substance from liquid phase to the gas phase. and that again occurs at the normal boiling point. And for water, that again is the heat of vaporization, the delta H of vaporization, sometimes referred to as the heat of vaporization. And as we go from liquid to gas, that is a endothermic process. And when we talk about energy, that is a positive value for endothermic, and it would be 40.7 kilojoules per mole. If I wanted to go from gas back to liquid for water, again, this is specific for water, it would be negative 40.7 kilojoules per mole. Negative energy values means exothermic and energy is being released. Takes the same amount of energy no matter which way you're going. The only difference is the sign, whether it's endothermic or exothermic. That translates for water approximately 2,260 joules per gram of water of energy is either released or absorbed at 100 degrees Celsius, which is the normal boiling point for water. By the way, these numbers here are specific for water. If you're doing some other substance, it will have a different value for the delta H of vaporization, and it may also have a different boiling point as well. So other substances don't always do that. Sometimes people think these are for every substance, but these numbers here, for example, are just for water. So other substances will have different heats of vaporizations and boiling point temperatures. So as I mentioned a second ago, in terms of the shower example, you do feel kind of warm when you're taking the shower because you do have a very big rate of evaporation happening. Condensation happening. But then you start to feel evaporation and you start to feel cold. Now, freezing and melting is obviously the process as we go from solid to liquid or liquid back to solid. For water, by the way, that occurs at the normal boiling point, freezing point, which is 0 degrees Celsius for water. Melting occurs when we take it from solid to liquid. That is a endothermic process. And freezing occurs when we go from liquid back to solid. That is a exothermic process, right? Now, at 0 degrees, at the normal melting point, say, of water, you have ice crystals happening. You have liquid water and ice at the same time. So again, it's not until you get a little bit above 0 degrees that you transition to liquid water, not until below 0 degrees that you are at solid ice. But we have sort of both phases happening in equilibrium at that point. That is also why, right, the process, if you just take an ice cube out of the freezer and you just put it on the table in room temperature, the ice cube is much colder than the room air. And that is how heat transfers. The hot air, which is just room temperature at this point, is going to go and be absorbed into the cold piece of ice and it's going to start to melt, right? That's why it just happens. We take it out, you don't have to do anything because of the difference in temperature of the room air and the ice cube. It will start to melt just by that process naturally. It's also how you make ice cubes, right? If you take room temperature water and you put it into the freezer, the room temperature water is hotter than the temperature in the freezer, and all the energy from the room temperature and heat from the water is going to leave those water that's you're trying to make ice from. And as it leaves, it's going to lose energy and go into the solid phase, and you will make ice. All that energy is released into the freezer air, and that is how you make your ice cubes, if you still make ice cubes nowadays. At this temperature, like I said, we will reach equilibrium at 0 degrees Celsius in the case of water. And as we've talked about a little bit before, water is an unusual substance. As you do that, for example, if you took your water and you put it into the freezer, again, the water is going to be a higher temperature than the freezer air. All the energy is going to leave the water, and eventually you'll make your ice cubes, creatively drawn as squares there now in my tray. And when water freezes, because of the really strong hydrogen bonding that occurs, in the solid phase, it does not have enough energy to allow these water molecules to get really close to each other. And what ends up happening is in ice, we actually get a lot of open volume between the water molecules because it doesn't have enough energy to get super close to each other. And that is why ice, for example, has a lower density than, say, liquid water. And that's very unusual for a substance. Usually in the solid phase, it has a higher density than the liquid phase. And if you think about density, which is mass divided by volume, these ice is really bloated with a lot of this open space. That's going to increase the volume. So you're going to take a small number divided by a large number. That's going to bring the density of our ice lower than you can in liquid water. In liquid water, they still have enough energy to actually get a lot closer than the water molecules to each other than they can when they have a lot less energy in the solid phase. And that is why, again, we see a little bit higher of a density in liquid water versus ice. Any questions on that there? Now, sublimation and deposition is the change of phase where we go from solid directly to gas and skip the liquid cleanup, or from gas back to solid. So sublimation is going from solid to gas. Deposition is going from gas to solid. And same idea, it is a endothermic process as you go from solid to gas, exothermic process as you go from gas back to solid. You may be familiar with sublimation, dry ice. If you've ever seen it, used it, dealt with it, you should be careful. It can burn yourself. But dry ice will actually go from solid directly to gas, no liquid cleanup. Dry ice, by the way, is not water, it's carbon dioxide. So that is what happens in that case. Deposition, they used to use for the process of, for example, one example was like CDs, DVDs. If you've ever seen any of those things, they're very, very shiny. They would use the process of deposition to deposit metals basically on the surface of those things. And that's how they got really shiny. Now, just like for going from solid to gas, there is also energy required to do the transition from solid to liquid, or liquid back to solid. That is the delta H of fusion. So the delta H of fusion is the energy required to simply take a substance from the solid state at its normal melting point to the liquid state, also has normal melting points. For water, that is 6.02 kilojoules per mole, or roughly 335 joules per gram. It is still endothermic going in this direction, so positive 6.02 kilojoules per mole. Exothermic going in the opposite direction there, minus 6.02 kilojoules per mole. The heat of vaporization is what we saw going from liquid to gas or gas to liquid. If you did that conversion like I did earlier, that's 2260 joules per gram. It takes a lot more energy to do the transition from liquid to gas than it does solid to liquid. You can see it's only 335 joules of energy to go from solid to liquid. The reason for that is as you go from solid to liquid, everybody is still relatively close to one another. They haven't completely broken apart from each other. So in the solid state, they're close. In the liquid state, they're still really close, but a little bit more energy. But as you do the transition from liquid to gas, you're going from something that's relatively close to each other to gas molecules, which are completely broken apart from one another and are flying around all the way with a lot of energy. So it takes always a lot more energy to do that transition going from liquid to gas than it does solid to liquid. Questions on that there? And that's what we see here. This is a heating cooling curve. Ice is solid. Liquid is obviously liquid, and steam here is the gas phase. And right here, as you can see in these plateau parts at 0 degrees Celsius, this is for water. That is where we would use our delta H of fusion. We also see over here at 100 degrees, which is the normal boiling point for water. That would be where we would use our delta H of vaporization. So as you do a phase transition, it actually occurs at the exact same temperature, but you are changing phases. The rest of the curve here is something that you might remember maybe from Chem, whatever they call that class, 100 maybe nowadays. That's maybe what they call it. These guys here, these are all processes where we actually are changing the temperature, but we're keeping the phase the same. So all through here, that's all gas. All through here, that's all liquid. All through here, that is all solid. Perhaps you might remember this equation. Maybe Q is equal to ms delta T, a little specific heat. And the specific heat equation is typically used to calculate the energy required to change the substance temperature while it's in the same phase. So if it's in the same phase and you change the temperature, it's a specific heat sort of question. If you are keeping the temperature the same but changing the phase, it's either a heat of fusion or heat of vaporization type of problem. Since we really don't do this until 200B nowadays, we don't have to worry too much about it, but that is how you would do the calculation. So if you wanted to figure out how much energy was required, for example, to go from say here, ice at whatever degrees, -5, to like steam at 100 and some odd degrees. There's actually several processes that occur as you go through it. The first process is you would have to take the ice from, say, -5 degrees to 0 degrees and figure out the energy required to do that. That would be like a specific heat equation. You then would have to do the phase change right here at 0, which would be your heat of fusion energy. You then would have to take the liquid water from 0 degrees all the way up to liquid water at 100 degrees. That would be another specific heat calculation. You would then do a phase change at 100 degrees from liquid water to gas, would be the heat of vaporization. And lastly, you would take gas at 100 degrees to gas at wherever that dot represents, and that would be a specific heat. So in that type of question, there actually is 1, 2, 3, 4, 5 different energy calculations that you would do using either heat of fusion, heat of vaporization, or specific heat. To get the total amount of energy, since energy is a state function, all you have to do is just add each step together, and that'll give you the grand total of energy to go all the way across there. All right. So let's talk a little bit about phase diagrams. And phase diagrams are helpful. They show our 3 phases and the 6 interconversions that occur between them. What are our 3 phases? Our 3 phases are solid, liquid, and gas. That's our 3 phases. The 6 interconversions are these: solid to liquid, melting, yeah. Liquid to solid, freezing. Liquid to gas, evaporation or vaporization. Gas back to liquid, condensation, as we talked about. Solid directly to gas, sublimation. Gas directly to solid, deposition. So phase diagrams will show all these 6 parts where solid, liquid, and gas is typically found. Now, remember again, melting and freezing occurs at the same temperature, normal melting point and boiling point. Evaporation and condensation also occurs at the same temperature, 100 degrees Celsius, for example, for water. It just depends on what you're doing at that point as to which way you go. If you continue to put energy in, you'll continue down the path of making gas, for example. If you take energy out, you'll go the other way and make solid. So as we go from solid to liquid to gas, those are again all endothermic processes. And as you go from gas to liquid to solid, those are all exothermic processes. So when we look at a phase diagram, it has the associated temperature and pressure associated with it. You will find actually on the phase diagram a point which is referred to as the triple point, And that is the point where you have all three phases basically occurring at the same time. It is basically your temperature pressure combination you would need to get all three of them to show up basically at the same time for that particular substance. Water has an unusual melting point line. It has actually a negative slope. And again, that's part of the reason why we do see ice having less dense than our liquid water. A couple other things that we will see on the phase diagram, we have what is known as critical temperature, and that is found at the critical point. And that's the temperature above where there's really no distinction between the liquid and the gas phases, basically. They kind of blend into each other at that point. There's also a pressure associated with that as well. That is usually represented on a phase diagram, sometimes as just simply the critical point. So it's just simply the critical point, and that's the temperature pressure combination where if you kind of go above it, it's going to kind of smear, if you will, the two phases. You're going to have sort of liquid and gas sort of happening at the same time. A supercritical fluid is where that occurs. That is where we're above that critical temperature. It has a density of a liquid, but will flow as a gas. And that's sort of in that area above the critical point where it kind of comes together is where you find that supercritical fluid. Here's a generic phase diagram. And typically speaking, we kind of go left to right, solid, liquid, and then gas is usually the setup there. This is pressure, this is temperature. And right here, as we go from solid to liquid, that is our melting transition. As we go the opposite way, that is our freezing. There's our vaporization. That is our condensation going from gas back to liquid. Down here at the bottom where this is basically solid to gas, we are not passing through the liquid portion here. That is our sublimation, and that is our deposition. Yeah, again, we're skipping the liquid phase at that particular point. By the way, the normal boiling point, the normal melting point is usually found at what type of pressure? A pressure of 1 atmosphere standard pressure, yeah? So if you go across and drew a better straight line than I did there, really where this crosses this line here, that would be where you find your melting point and boiling point temperature if you went down on the X. And obviously where it crosses here is where you'd find your boiling point as well. This is the triple point right here. That is where we have really all three phases happening at once. That gives you your kind of temperature pressure relationship that you would need for that particular substance to do that. Up here at the end of this line right here between liquid and gas, that's the critical point. That's where we find our critical temperature over here and our critical pressure. And above that, you can see that is where we find that supercritical fluid. Has a density of a liquid but flows like a gas, because as you can see, it's able to go just from the liquid right into sort of the gas phase over here with no problem at that point. Any questions on that? So obviously, you do need to know where all those phases are, where melting, boiling, freezing, all those things are, triple point, critical pressure, where the supercritical fluid is. If we take a look at one here, this is actually carbon dioxide or dry ice. And we see our solid, liquid, and gas. This is our triple point right here. So that is the pressure temperature combination, again, that would be needed for us to see all three phases. Dry ice, which is carbon dioxide, as I mentioned before, goes through sublimation, right? It goes from solid directly to gas, skips the liquid part. That is because normal pressure is 1 atmosphere. And if I draw a line across my normal pressure, at no point do I cross the liquid phase, right? I do not cross the liquid phase on this diagram because I don't have the right pressure to do so. If I wanted to force dry ice to become liquid, what type of pressure would I need? I would need a pressure that is above this number, right? That would get me somewhere up here. And I would also need a temperature, out in this area, right? So you could get it to do so. So that's like 5 atmospheres, which is like 5 times normal pressure. So that's why we don't normally see dry ice become liquid, right? Under normal conditions, unless you're in a really bad pressure situation, right? So you need some serious pressure to try to force CO2 or dry ice into the liquid phase. And again, that's why under normal conditions, we don't see it actually pass that way. Pressure temperature relationship doesn't work for us. Any questions on that there? All right, so using this one for CO2, for each of the following conditions, decide what type of phase we would expect things to end up in. So take a few moments there and decide what phases should each of these be in under these conditions. Okay, let's take a look. So first one is 20 degrees Celsius and 72.9. So I'm going to say here, this is 72.9. And 20 degrees, that's 31 over here. So I would think we are back a little bit. So I would say probably somewhere in that ballpark. And that should be our liquid phase in this case. We got minus 56.7, which is here. And we got 5.1, which is right there. And that is our triple point. And that is the point where we have everybody happening at once. All three phases are basically occurring at this point. If we go to 10 degrees Celsius, which I guess would be somewhere in this ballpark, and 1 atmosphere, which would be right about there, so somewhere in this ballpark, would put us in the gas phase. At minus 78.5, which is right there, and 1 atmosphere puts us right there, I believe, on that line. And that is the line between solid and gas. And right on that line, we would have both phases happening at the same time at equilibrium. And we would have solid and gas happening in this case. And lastly, here at 50 degrees, which would be beyond the 31, I would imagine, and 80 degrees, which would be above here. So that would probably put you right about here. That is above our critical point where our critical temperature and pressure is at. We would have a supercritical fluid probably at that point, is what we would have. That would be our guy that is density of liquid but flows like a gas, right? That's the point, as you can see, just kind of flays through there. Any question on any of those there? All right, we're going to lay it up there